I think it'd be good to do a couple more examples looking at rigid body kinematics. And one of the things that I'll point out here as I sort of rush through these problems is that the point of this lecture is not so much to explain all of the steps, but it is to encourage you to do these problems on your own and use this as a guide to help you solve the problems. And again, one of the biggest problems with rigid body kinematics is not so much the problems, but doing enough so that you're comfortable with all of the ideas associated with it. So we have here a 3-bar linkage, and that linkage consists of a link AB, link BC, and link CD. You're given a set of distances A to C of 1 meter, C to D of 2 meters, D to C of 1 meter, and C to B of 1 meter. As well, the link AB has a length of 2 meters. I'm trying really hard to make sure I do this every time. X, Y, and my positive rotation. Omega AB is given as 4 rads per second. Alpha AB is minus 6 rads per second squared, which means it's clockwise. Alpha BC and alpha CD are the unknowns, and you're asked to find them. So you only have a little bit of information here. You need to find the angular velocities of the two other rods, VC, VB, VC equals VB plus VC relative to B. So you can do omega CD cross with RCD right here. And you can do omega AB cross with RB with respect to A right here. And then finally BC over here. The thing to note is that CD, AB are fixed point rotation, so they are easier to define often. The one that's challenging or the more difficult one is BC, so that's why you're sort of keeping it as one separate term. Everything else, these two terms, VC, VB, are defined in terms of fixed point rotation. And then the last one is actually a rotation term, but it becomes a set of unknowns. I also can kind of guess what I expect to have as the velocities. I expect that AB is going to go up, so or clockwise or counterclockwise, and so that VB is going to be upwards. And the link CD, again, velocity is going to be normal to that, and it's going to go up and towards the right. So if I put in my terms of omega CD cross with minus 2, 1 meter, tack. So from D, minus 2 plus 1, omega AB is plus 2 meters, and omega BC is minus 1, minus 1. This is against the coordinate system I've defined at the top. That's helpful to me because I often will forget these things as I'm going through these solutions. And then I calculate omega CD, which is 2.667 clockwise, 2 2/3 clockwise, 2 2/3 counterclockwise. And you can see that rotation here. You'll notice that I didn't put negative here because I've defined this as clockwise, so that sort of takes care of the magnitude. So now I want to solve for all of the accelerations in the system, and if I do that, I already know that alpha AB is 6 rads per second squared clockwise. I know that the distance from A to B is 2 meters. So acceleration of A is equal to 0 because it's fixed. Alpha AB cross with RB with respect to A is 2 meters, and I've been given this. And in the previous part of the problem, I was given the omega AB. So I have all of the terms plus 2 meters, and just recognize that what I have here is acceleration tangential and acceleration normal. If I go to the next part of the problem, and I didn't plan to do it this way, but acceleration C equals acceleration B plus alpha BC cross with RC with respect to B minus omega B squared RCB. Here, it's going to be minus 1, minus 1. So it's minus I minus J. Put in the terms, do all the calculations, and I get this expression where my unknowns are alpha BC. Finally, the acceleration of D is going to depend on the acceleration of C plus alpha CD cross with RD with respect to C minus omega CD squared RDC. So minus 1 plus 2. So 2I minus J here. Put in the terms, and I have my unknowns. So the acceleration of c I got from the previous part up here. I have the acceleration of c with respect to d, and now I have two unknowns, and when I do all of the sort of manipulations, I have two equations and two unknowns, one in I and one in j. Substituting in terms, solving through for the unknowns, I will have alpha BC, which is 26.8 rads per second squared counterclockwise, and alpha CD, which is 12.3 rads per second squared counterclockwise. So there you go. So it's kind of a neat result, and again, very complex motion. There's a lot here, but very careful walking through the problem. Make sure that you actually get it right. Here's another problem, a little bit different. I have a slider at C, which is constrained to move left or right. I have a rotating rod at A, with alpha AB of 8 rads per second squared and alpha or omega AB of 2 rads per second squared. Again, I'm being really good here. I'm putting in my coordinate system on each of these plots. Distances can be given to you: 0.32 from A to B, 0.24 from B to C, and 0.16 from C to D. In this dimension, 0.48 from B to C and 0.32 from C to D. So what is omega BC? Well, you have for the link B, C, and D, general plane motion. For the slider C, it's translation, and for AB, it's fixed point rotation. Omega AB is 2 rads per second. So velocity of B is equal to velocity of A plus omega AB cross with RB with respect to A. Velocity of A is 0. And substituting in terms, you get 0.64 meters per second in the j direction. Makes sense. And it's upwards. For velocity of c, it's equal to velocity of b plus omega bc cross with rc with respect to b. Distances are given. Velocity of b is 0.64 j. Omega bc is given 0.24, 0.248. So substituting in terms, now I have two expressions for I and j. Solving through, I find omega BC is minus 2.67 rads per second. What is the acceleration? And so again, I'm given alpha AB, which is 8 rads per second squared counterclockwise, as shown here. Coordinate system is shown. Acceleration of B is equal to acceleration of A plus alpha, the acceleration tangential, and the acceleration normal. So I put in the terms, 8 rads per second squared, k, 0.32 meters, which I have as the distance, and 2 rads per second, 0.32 meters I. So again, same thing as before. And I end up with minus 1.28, 2.65 j meters per second squared for the acceleration of B. So again, 0.32 meters. Substituting in terms and sort of messing this up, alpha BC K, 0.24 I, 0.48 J. Substituting in all the expressions, I then end up with an expression with one unknown, alpha BC, which is the same as alpha BCD. So there you go. And those are the distances. Again, I'm not looking at the directions of velocities. I'm not looking at the directions of accelerations. I'm only looking at positions on the diagram. And I can do that in my head. Well, I can't do it in my head. I can do it pretty easily on the figure. And I don't have to rotate anything or think too hard in that one. So if I substitute in terms, and I know that C can only move in the x direction, I end up with 3.56 rads per second squared for alpha BC. So I know it's counterclockwise, calculated all the terms. For the acceleration at point D, that's equal to acceleration of B plus the tangential acceleration and the normal acceleration. Substituting in all of the expressions I already have and all of the terms I have, I already know what the angular acceleration of BC is. I already know what the omega of BC is. And so I have a total acceleration there. And the result is that I have acceleration of D, which is minus 0.697, minus 1.71 meters per second squared. These are very hard problems. I can't go over this enough. They're always difficult. Practice is crucial. Make sure that you do a lot of these problems so that you get comfortable with it. Once you've done enough, you'll actually be pretty skillful at this. And it's just making sure that you kind of learn how to visualize things. Thank you very much, and we'll talk again later.